Hi, I'm Weifang Sun. Today I would like to introduce our work, Training Energy-Based Normalizing Flow with Score Matching Objectives. Let's start from the background of normalizing flow. Normalizing flow, or flow-based model, is a type of generative model that can simultaneously support fast sampling and density estimation. This type of model is formulated based on the change of variables theorem, where the probability density is normalized by the Jacobian determinant of the transformation. Typically, flow-based models are trained by maximum likelihood objectives, where the computation of Jacobian determinants are required, and is often the computational bottleneck. The Jacobian determinants can be expressed as the product of the Jacobian determinants associated with different types of layers. The neural network often contains linear and nonlinear transformations with big O of d cubed and big O of d time complexity respectively. The d here corresponds to the data dimension. The computational bottleneck lies in computing the Jacobian determinants of the linear layers. To reduce the computational cost of the Jacobian determinants of the linear layers, prior works can be categorized into two types of solutions. The first type of solution designs special linear layers with Jacobian determinants that can be easily computed. These solutions sacrifice architectural flexibility to reduce the time complexity. The second type of solutions uses special optimizers to directly approximate the gradients of the Jacobian determinant terms. This type of solutions introduces an error term to reduce the time complexity. Our work takes a different perspective by establishing a connection between flow-based models and energy-based models. We first identify the input-independent multiplier, which is the Jacobian determinant of the linear layers. This input-independent multiplier corresponds to the normalizing constant of energy-based models, which can be bypassed by applying energy-based objectives. We name this approach as energy-based normalizing flow, abbreviated as EB flow, which allows more efficient training when using general linear layers. In this table, we can see that the score matching objectives, which are commonly used in the energy-based model literature, have lower time complexity than maximum likelihood objectives. In particular, the slice score matching objective is unbiased comparing to relative gradients and is unconstrained when compared to specially designed layers. However, directly applying the score matching objectives may exhibit decreased performance. This is due to the logic preprocessing layer commonly used in flow-based models. It has extremely large derivatives near 0 and 1. To tackle this issue, we propose to match the preprocessed distribution to improve training stability and prove that this match after preprocessing technique is valid. Another technique is applying exponential moving averaging, which can stabilize training by utilizing an additional set of shadow parameters that can smooth the parameter updates. To analyze the scalability of our proposed method, the figure on the left here shows the runtime versus the data dimension when training with different objectives. Score matching based objectives exhibit better scalability when compared to maximum likelihood objectives. The figure on the right here shows the performance versus the training time. Score matching based objectives converge faster when compared to maximum likelihood objectives. To validate the performance of EB flow, this table shows that our method achieves lower complexity or improved performance when compared to the baselines. The figure at the left here shows that we can generate better qualitative results when compared to previous work using score matching. The figure on the right here shows that we can perform imputation by treating the flow-based model as an energy-based model and perform Markov chain Monte Carlo sampling. To sum up, this paper has three main contributions. First, we establish a connection between the parameterization of flow-based and energy-based generative models. Second, we bypass the computation of Jacobian determinants for linear transformations using score matching objectives. And finally, we enhance training stability and performance through a number of techniques, such as match after preprocessing and exponential moving averaging. Thanks for listening. If you want to look further into this paper, please scan the QR code below for the full paper and the source code.